inside, the inner function stays inside. So you differentiate the outer function, leave the inner function inside, but then you must multiply by the derivative of the inner function. Okay? And that's why it's a chain, right? It's a chain of multiplication. So you're always multiplying by the derivative of the inner function. So in our case, where f composite g is the square root of x cubed minus 1. If we follow the logic through, then to construct the derivative, we would need to take the derivative of the root function first. Right? That's the outer function. The outer function is the root function. So f prime with respect to x is going to be what? I need to take the derivative of the root function. What do you say? It's a 1/2 power. I will treat it as 1/2 power. And I'll use a power rule on it, okay? X is the 1/2. So I'll use a power rule on it. Every radical is some sort of rational power, right? Yeah. Okay. So bring down the 1/2. Right? Lou, you're telling me. Go ahead, tell me, Lou.
1/2 x to the negative
1/2 x to the negative 1/2. Now we'll rewrite that using the radical notation. Be 1 over 2 root x. Okay? Everybody okay with that? Right, that's the derivative of the outer function. I also need the derivative of the inner function. So I'm going to take g prime. So that's the derivative of the x cubed minus 1, right? That's a little bit easier. 3x squared. So to put the pieces together, this is not the general way you're going to take this derivative, right? It's not the general way. It's a little inefficient right now, but just want to put all the pieces together. You can kind of see how it goes. So I need to take f prime. There it is. F prime, but in place of x, I need to see the original inner function, okay? So in this case, f prime g inside times g prime is going to be 1 over 2 the root, right? Root of x, but x doesn't sit here, g of x sits there. So g of x is x cubed minus 1. So we have x cubed minus 1 sitting inside there. And we multiply this whole thing by the second derivative we took, g prime, and that is 3x squared. Okay? We might make it look a little bit nicer. This is 3x squared above 2 root x cubed minus 1. There's our derivative of this particular composition. Chan, you're looking at it pretty solid. Something.
No, I gotta get it.
Okay. Number 11. Y equals tan of 5x squared. Composition or not a composition? Composition. What is the inner function? 5x squared, and the outer function is tan. Okay? So to take the derivative of this, what we need to do is first take the derivative of tan, right? It's the derivative of outer. The derivative of outer is the first thing you're going to do. So what's the derivative of tan? We talked about it last time. Secant squared. So when I want dy dx here, I need to have a secant squared, but it's not secant squared x, right? Because I maintain the inner function inside that derivative I take, right? This part here still has the inner function inside. So it's going to be secant squared of 5x squared, right? 5x squared will still be sitting inside here. Okay? Times 10x. You say 10x? 10x. Times 10x, that's right. Times the derivative of the 5x squared. So times 10x. And in general, it's better if you write the 10x out front so you don't get confused and think that it's somehow part of the argument of secant squared. So it will look like this. Okay? Follow that okay so far?
That's the answer?
That is the answer. Now, these chains can become as long as they need to be. This is only a single composition. I only composed 5x squared inside of tan. But this could have been put inside an exponential function, which could have been inside another trig function, could have been inside another polynomial, right? And the changes, so you're always just taking the next step, derivative inner function. Next step down, derivative next inner function. Next step down, derivative next inner function, right? And keep multiplying on, multiplying on. The chain can be as long as it wants to be, right? I'm going to start with just a 2-link chain here. Make this as easy as possible. 15. But I hope you can kind of get a feel for the vast amount of functions that this is going to take care of for us now, right? Vast amount of functions that we can now deal with. We can deal with composition. What did I say, 15?
Yeah.
E to the negative x squared. Okay? Again, I'm claiming it's only a 2-link chain for the most part, so there's an inner and an outer. So what's the inner?
E.
No,
X squared.
Negative x squared is the inner. The negative x squared has been put inside e to the x. So if we wrote it in terms of f and g, I would say that f, the outer function, which I'll try to always use it in that context, f will always be outer, g inner. If f is the outer function, then f of x is e to the x, and g of x, the inner function, is negative x squared, and we're looking at this as being f composite g. Okay? Okay? A lot of these are visual, and to see what is inner and what is outer. So a lot of times parentheses give it away. In this case, there's no parentheses, so it may not have been quite as obvious. Okay. Fine. So in terms of derivative, we need to first take the derivative of f. So what's the derivative of e to the x?
E.
E to the x. So it has to come back. So dy dx is going to be e to the x, but it's not just going to be the x there, right? You're going to maintain whatever the inner function was a second ago. So e to the negative x squared is going to come back the entirety of it. Okay? So e to the negative x squared comes back. Now we need to multiply by the derivative of the inner function. So negative 2x, right? Times negative 2x down here. And again, it will look better with the negative 2x out front, e to the negative x squared. That's our answer.
Rule for E when it has a power of time. Take the derivative of that power, right?
That's what I explained last time, right? That's right. What did we do last time? We had this very special case at the end of one of the classes. We had e to the kx. What was its derivative? K e to the kx. And I said the way to view this is what you did was you multiplied this by the derivative of the exponent. The derivative of kx is just k, right? Now you see why, because it's really just a chain rule. Kx is the inner function, e to the x is the outer function.
So K
Say it again.
K was going to be out front.
Well, it may not always be k. Here there's no k, right? This is negative x squared. It's not even linear here. This is already a quadratic inside. But it's the same idea. Take the derivative of kx, you get k. So that's why you have it sitting there. Just like you have the negative 2x sitting here. Derivative inside multiplied, right? That's all you're doing. The derivative of kx is k, so you have to multiply by that. Number 14.